questions 21 through 25 on the 2016 Grade 12 AMC 12A. A quadrilateral is inscribed in a circle of radius 200 times root 2. 3 of the sides of this quadrilateral have length 200. What is the length of the fourth side? Here is a diagram. Here is A, B, C, D. And then we are given a few of these. This is 200, this is 200, and this is 200. And in particular, we also are given the radius. Now, to put the radius on the diagram, I've got to draw the center. So probably here, and then let's just draw 2 radii, one to there and one to there. And now those red lines that I just drew have a value, 200 root 2. So I'll just put that up here instead of making the diagram messy. So those radii that are represented by the red line, and this is C for center. And then this point where it crosses, I'll write E and then F, like that. And just for the sake of completion, I will draw a couple more lines from A to C and from C to D. And I think that should be sufficient. Now, what we have to do in this question first is a whole bunch of angle chasing. And angle chasing is basically labeling angles, right? Like this is a theta, so that's theta minus 90 or whatever, right? And what that angle chasing will eventually make us conclude is that there's a bunch of similar triangles here. Okay, so let's begin. And I'm not going to walk you through it because, you guys know how to do angles in triangles. The sum is 180 and, you don't need me to walk you through it. Well, this triangle right here is isosceles since those are radii. So that means if this is theta, this is theta. And then this guy right in here would be 180 minus 2 theta. Okay? So that's the beginning of it. And then very similarly, this is also an isosceles triangle. So this is theta and this is theta. All right? And then the next thing, same kind of story here. This guy in here, right here, would be 180 minus theta, like that. And then similarly, this and this are also theta because basically it's the same triangle. This is the same as the other one, this guy. They have the same side lengths, two radii and 200. So this is theta, and this whole thing is theta. And therefore, this guy in here would be 180 minus 2 theta, like that. And then you can figure out this angle in here by subtracting from 180 this and this. And when you do, you get 3 theta minus 180. And then you can figure out this angle by subtracting from theta 3 theta minus 180. And when you do, you get 180 minus 2 theta. This guy in here. 180 minus 2 theta. And then finally, this angle you can get since we know the other two. And when you do, you find that's theta. So I'm sure you guys are very well versed in angle chasing. But what does in this question is allow us to conclude that triangle ABE is similar to triangle CEF. And in particular, ABE is this one right here. It has 180 minus 2 theta, theta, and theta as the angles. And triangles CEF. CEF is also 180 minus 2 theta and theta and theta. So that is basically what I wanted to, illustrate. Okay, since those two triangles are equal, or they're similar, or whatever you want to call them, they're not equal, they're similar. The ratio of the sides will be equal. So AB over BE will be equal to EC over EF. And that is equal to CB over BC. All right, let's see what we know. AB is 200. BE I don't know yet. EC I also don't know yet. And EF I also don't know yet. CB, that's the radii, and that's 200 root 2. And BC is 200. Okay, great. So I can systematically now calculate each of these. This equals that, so I can figure out what is BE. That would be, let's see here, 200 over BE is equal to this, which is just root 2. So that means that BE would be 200 over root 2. And when you multiply top and bottom by root 2, you get 100 root 2 for BE. Okay. EC, I think I can figure out from this now that here's EC right here, from here to here. And since we know BE, we can figure out EC. EC is basically BC minus BE. And BC is just the radii, so that's what, 200 root 2? And then BE we just figured out was 100 root 2. So that means EC is 100 root 2. Okay, and then finally we can figure out EF using this equation right here. We've got EC over EF is equal to root 2. EC is 100 root 2 as root 2 EF. So that means EF is equal to 100. All right, we're done. Final step. The question asked us to figure out the length of the fourth side of that quadrilateral, and that is AD. Well, AD looks like it's equal to AE plus EF plus FD all the way across. AE is from here to here, which is the same as from here to here, since that was isosceles, since these two angles were the same. So that means AE is the same as AB, which is 200. EF we actually got right there, so that's 100. And then FD, because of the symmetry of this diagram, you'll be able to show that FD is the same as DC. So that's 200. And therefore, adding it all up, we get AD is equal to 500. And 500 for number 24 is choice E. How many ordered triples XYZ of positive integers satisfy least common multiple of x and y is 72, LCM of x and z is 600, and LCM of y and z is equal to 900? We are given a few clues. Lowest common multiple or least common multiple, whichever way you'd like to say it, is 72. So I'm going to break this up into its prime factors. I think that will be most helpful for us. 72 is what? 2 to the power of 3 times 3 squared. All right, moving in the same way, the next one is xz, and that's 600. So that means LCM of xz is the prime factor of 600 would be 2 to the power of 3 times 3 to the power of 1 times 5 to the power of 2. And then the LCM of the next one is YZ, and that's 900. So breaking that up into prime factors, we would get 2 to the power of 2, 3 to the power of 2, and 5 to the power of 2. Okay. So what I'm going to do is use some triangles to kind of illustrate all this. I hope it helps. So if you have x, y, and z, let's see what we get. Well, x and y have a least common multiple of 2 to the power of 3, 3 to the power of 2. And then x and z, 2 to the power of 3, 3 to the power of 1, and 5 to the power of 2. And y and z are 2 to the power of 2, 3 to the power of 2, and 5 to the power of 2 with regard to their least common multiples. All right, so now what we want to do is take a look at this one prime number at a time. So first, let's just start off with the 2's. And we'll then talk about 3's, and then at the end we'll talk about the 5's. So let's just look at the 2's. Well, it's 2 to the power of 3 here, 2 to the power of 3 here, and 2 to the power of 2 here. 2 to the power of 3, 2 to the power of 3, 2 to the power of 2. Okay, so that obviously means that x has a 2 to the power of 3 as part of its factors. It might be entirely equal to 2 to the power of 3, or it might have 2 to the power of 3 as part of its factorization. But regardless, it definitely has 2 to the power of 3. So now I've got to figure out what is y and z. Well, they have a LCM of 2 to the power of 2, so we've got a few choices here. It could be 2 to the power of 0 for y and 2 to the power of 2 for z. Or it could be 2 to the power of 1 and 2 to the power of 2. Or it could be 2 to the power of 2 and 2 to the power of 2, 2 to the power of 2, 2 to the power of 1, or 2 to the power of 2 and 2 to the power of 0. Any of these would satisfy y and z having an LCM of 2 to the power of 2. And as you can see, there's 5 such ways of arranging y and z, or creating y and z. All right, so now that's pretty good. Let's move on to the next one. The next one will be talking about 3's. So here's x, here's y, and here's z. And now I've got to put 3 to the power of 2, 3 to the power of 1, and 3 to the power of 2, like that. So 3 to the power of 2, 3 to the power of 2, and 3 to the power of 1. So obviously y is equal to 3 to the power of 2, meaning 3 to the power of 2 is part of y. That's pretty obvious. Now I've got to figure out x and y. Well, x and y, a few choices, right? We can have either 3 to the power of 1 for x, and z could be 3 to the power of 1 also. Or you can have 3 to the power of 0 for x, and 3 to the power of 1. Or you can have 3 to the power of 1 here, and 3 to the power of 0 here. I think those are the ones that would be the only ones. Yeah. So that means this combined with this gives me 3 possibilities. 3 arrangements for x and y. Either this guy with this guy with this guy, or the 3 to the power of 1 with 3 to the power of 0. So that's 3. Okay, so I think I'm getting close here. One final triangle, of course, and that's got to look at the 5's. So let's look at the 5's now. So here we go. X, y, and z. And let's see if I refresh my memory here. There was no 5 here, 5 to the 2 and 5 to the 2. Okay, so that means 5 to the power of 0, 5 to the power of 2, and 5 to the power of 2. So that means z must be my 5 to the power of 2. And then the combinations for x and y, x can be, well, there's only one choice, 5 to the power of 0, and y 5 to the power of 0 for x and y, these two. That's it. So that means I've only got one possible way of setting up x and y with regard to powers of 5. Okay, so I'm ready to figure out the total number of cases. 5 number of cases for the 2's. Multiply that by 3 cases for the powers of 3, and multiply that by the 1 case for powers of 5. And 5 times 3 times 1, of course, is 15. And that is the total number of ordered triples, x, y, z, that satisfied the conditions of the question. So number 25, the answer is A. 3 numbers in the interval 0 to 1 are chosen independently and at random. What is the probability that the chosen numbers are the side lengths of a triangle with positive area? We have something known as the triangle inequality, and I'm sure you know about that. And it basically says that if you have 3 sides, x, y, z, the only way you can make a triangle is if x plus y is greater than z. So this is the way to make these triangles. But if z is, say, greater than or equal to x plus y, then the triangle inequality fails. So let's first put this whole thing on a coordinate plane, x, y, and z. So we have a 3D coordinate plane, x, y, and z like that. And this is, of course, x, and this is y, and here we have z. And our boundaries are 0 to 1. So that's the maximum that anything can be is between 0 and 1. So let's draw that in. And of course, this is the origin. And this point right here would be 1, 1, 1. So it's a cube, basically, that describes all the possible choices for x, y, and z, the three parts of the triangle, the three sides of the triangle. Now let's concentrate on this region, and this takes a little bit of thinking. Any x, y, z that satisfies that would mean that it would be a triple that lies above z is equal to x plus y. And in particular, with regard to the cube, we have to define some boundaries, and those boundaries are going to be 0, 0, 0, 0, 0, 1, 0, 1, 1, and finally 1, 0, 1. So let's plot those. Plotted on the cube, it's these points right here. And that is the region that you would basically get the triples that would fail to create a triangle. So let's connect those and see what kind of a shape we get. If we connect those, you will see that it is the shape of a tetrahedron. And we can, of course, figure out the volume. That's going to help us with the probability. So the volume is going to be, as always, 1/3 the area of the base times the height of the shape. Well, 1/3 the base is just this guy right here, which is a triangle, 1/2 1 times 1. And the height is from here to here, which is obviously just 1. So this looks like it is 1/6. All right, but here's the thing. The same holds true for any region involving x less than y plus z, and also y greater than, I should say, x plus z. So if x is greater than y plus z, or y is greater than x plus z, it's similar to that. And each of these volumes are also going to be 1/6 by the same sort of calculation. So to calculate the total regions that fail to produce triangles, it's this plus that. And that's obviously 3/6, which is a half. But we don't want the ones that fail, we want the ones that succeed. So if you want the ones that succeed in creating a triangle, you'd have to subtract this from 1. And when you do, you get a half. And that is the answer to the question. So number 23, the answer is C. There is a smallest positive real number a such that there exists a positive real number b such that all the roots of the polynomial x cubed minus ax squared plus bx minus a are real. In fact, for this value of a, the value of b is unique. What is the value of b? Well, if this polynomial has roots, we can call them r1, r2, and r3. And when you factor it out like that, it would equal the polynomial, which is x cubed minus ax squared plus bx minus a. Well, let's expand this, and I'll just do the full expansion to save a little bit of time, but I'm sure you could do that full expansion. It's going to be the following if you collect like terms. R1 plus R2 plus R3 has the coefficient of x squared. And then R1 times R3 plus R1 times R2 plus R2 times R3. And that is the coefficient of x. And then finally R1 times R2 times R3. And that is, of course, equal to the right side. Now let's look at each individual coefficient. So this guy obviously is my A. So R1 plus R2 plus R3 is equal to A. This whole thing is equal to B. So R1 times R3 plus R1 times R2 plus R2 times R3 is equal to B. And this is equal to A. So R1 times R2 times R3 is equal to A. So there we go. Now what we have to do is use something called AMGM. If you're not familiar with AMGM, not a problem. I'll explain it. AMGM means arithmetic mean, geometric mean. And it has a very unique formula, and that formula is as follows. If you have two numbers and you take their arithmetic mean, it will be greater than or equal to the geometric mean, which is the two numbers multiplied under the square root sign. If you have three numbers, a plus b plus c, then the arithmetic mean, of course, you divide by 3. But the geometric mean would be a times b times c, but this time you take the cube root. So that is AMGM, and that's what we're going to apply. So using, of course, this guy, since we have 3 roots, we can get the following. That if we add up the roots, R1 plus R2 plus R3, and then divide by 3, that's going to be greater than or equal to R1 times R2 times R3, the cube root. So exactly what is written there. Okay, well, let's start to simplify this. The first thing we can do is cross multiply. R1 plus R2 plus R3 is greater than 3 times the cube root of R1 times R2 times R3. And then we might as well plug in the values of A. So this whole thing was A. So that's A right there. And then this is going to be 3 times the cube root of A, because R1 times R2 times R3 is also equal to A. All right. Now I want to get rid of that cube root, so I'm going to cube both sides. And when I do, I get a to the power of 3. And on this side, this is going to be 27, and then just times A. Divide through by A, and we get a squared is greater than or equal to 27. And that means A is greater than the root of 27. And the root of 27 is 3 root 3. All right, so we made some pretty good progress there. We know that A's got to be equal to or greater than 3 root 3. So the smallest possible A is equal to 3 root 3. And therefore, when we look at these two equations, you will hopefully come to the conclusion that the only way that R1 plus R2 plus R3 is equal to A, which is 3 root 3, and R1 times R2 times R3 is equal to A, which is 3 root 3, is if and only if IFF R1 is equal to R2 is equal to R3 is equal to root 3. It's the only way that's going to work. So now we can figure out B, since we have identified the values of R1, R2, and R3. B is R1 times R3, so that's root 3 times root 3, plus R1 times R2, which is root 3 times root 3, plus R2 times R3, which is root 3 times root 3. And therefore this is 3 plus 3 plus 3, and that is equal to 9. So we get a unique value for B equal to 9, and therefore number 24, the answer is B. Let K be a positive integer. Bernardo and Sylvia take turns writing and erasing numbers on a blackboard as follows. Bernardo starts by writing the smallest perfect square with K plus 1 digits every time Bernardo writes a number. Sylvia erases the last K digits of it. Bernardo then writes the next perfect square. Sylvia erases the last K digits of it. And this process continues until the last two numbers that remain on the board differ by at least 2. Let f at k be the smallest positive integer not written on the board. For example, if k is 1, then the numbers that Bernardo writes are 16, 25, 36, 49, 64. And the numbers shown on the board after Sylvia erases are 1, 2, 3, 4, and 6. Thus, f at 1 is equal to 5. What is the sum of the digits of f2, f4, plus f6, plus ... f at 2016? Let's begin. So this is Bernardo And this is Silvio or Sylvia. And then here I will put what value of k. Here I'll put f at k. So Bernardo, Sylvia, k, and f at k. All right, so let's start discussing this. The first scenario is when k is 1. They give you that in the question, but it's worth talking about. Bernardo is going to write, perfect squares starting with the 1, 2, 3, and so on, right? And eventually he's going to write 49 and then 8 squared, which is 64. And then Sylvia always is going to erase k digits. So removes k digits, always. K in this case is 1. So this one, when you remove the 9, you'll just get a 4. And when here you remove the 4, you'll get a 6. So as you can see, when this table continues with Sylvia, the 5 is missing. So therefore, the value of f at 1 is 5. It's the number that, the smallest number that doesn't appear in either list. Okay, so hopefully that's pretty straightforward. Now let's move up to k equals 2. Okay, so here we have 100 squared, or 100 actually, and then 121, and then you keep on going. The numbers that will be for Sylvia will be 1 and 1. And then eventually what will happen is you'll get up to 59 squared. And 59 squared is 3481. And then when you remove 2, Sylvia, her number becomes 34. And then next one is 60 squared, which is 3600. And when we remove those two numbers, you get 36. So as you can see, there's a 35 missing. And therefore that is the value of f at 2. F at 2 is 35. But we've got to, if possible, I know it's pretty early to do this, kind of get some sort of a pattern. Well, I'll just do what's obvious. This 6 goes to 5, so it's always going to be 1 less. This 36, that means f at 2 is 35, so again 1 less. All right. And this 60, although you might think, well, how on earth did you get that, is really 50 plus 10 squared, right? 60 squared. And you might say, well, there's no way I would have been able to see why that's important at this stage. Well, hopefully in later stages it will become more obvious. Okay, let's continue. When k is 4, because remember, we have to figure out f at 2, f at 4, f at 6, and so on. So we got to get some sort of a pattern with even values of k, 2, 4, 6, 8, like that. When it's 4, we have 100 squared, which is 10,000 as my initial. When I remove 4 digits, remember you're always removing k digits, you get 1. The next one will be 101 squared, which is 10201. Again, remove 4, you get 1. And then this process continues until you get to 5099 squared, and that is 2599 9801. And when you remove these 4 digits, you get 2599. Sylvia gets. And then the very next one is 5100 squared, and that is 2601000. So when you remove those 4 digits, removing them, you get 2601. So as you can see, the number here is missing, 2600. So that means that f at 4 is 2600. And I am fully aware that that is quite difficult and quite time consuming. So let's put in our stuff that we can get, 1 less, okay. Now we got to figure out this number here. Well, 5100 is the same as 5000 plus 100 squared. So I don't know if you can see a pattern, but hopefully a pattern is kind of emerging. Let's keep going. So I'm going to do 6, and then I'm going to do k, and then I'm going to write in general. So in general, that kind of stuff, because already it's so time consuming. Okay, let's go to 6. I think my pattern is as follows, that you add 2 zeros to the number that begins with the 5. So I'll call that to the 5 number. This guy right here, this is the 5 number. And then you add 1 0 to the number that begins with the letter 1. So I'll call that the 1 number. So you notice here, to go from 50 to 5,000, I had to add 2 zeros. To go from 10 to 100, I had to add 1 0. So I think that my perfect square, my last perfect square that I got to put into these tables on this one is going to be 5,000, add 2 zeros. So that's going to be 5,000,000 plus 100 plus 1 0, so 1,000, all squared. And when you expand that monster, you get 251,001,000,000. And remember, you're removing k digits. K in this case is 6. So when you remove those digits, you get 251,001. And f at k is always 1 less. So f at k, in this case, will be f at 6 we're really talking about. It's going to be 1 less than that number. So that would be 251,000. Right? Okay. All right, let's do one more. And I think one more is enough. Again, use this pattern. And when I do, I will get the last perfect square in this list to be 5,000,000, adding 2 more zeros, right? So 0, 0 plus 1 more 0 to that. So that just becomes 10,000. Square that. Expand that. It's going to be, oh boy, 250,100,10000, and another 40,000,000. We're removing 8 this time. So let's see here. We're going to remove these guys. And when you do, Sylvia's number becomes 2501,000,001. And to get that, we go 1 less, as before. And therefore, f at 8 is 2501000. All right. I think I'm convinced with that. Okay, so now we have to see any kind of a pattern with these f at k's. Well, this one here is 35, and that one is 25 plus 10, that 35. This one was 2600, and 2600 is 2500 plus 100. The next one was this guy, and 251000. That can be written as 250,000 plus 1,000. And then this guy here can be written as 250, how many? 6 zeros, right? 1, 2, 3, 4, 5, 6 plus 10,000. Okay, so finally I've got my in general. In general, it's going to be f at k will be equal to 25 times 10 to the power of k minus 2 plus 1 times 10 to the power of k over 2. Okay? Now you don't really need to figure out a formula, but if you can, it's helpful. Okay, so now let's figure out what they want me to figure out, which is a big long sum. And that big long sum is as follows. F at 2 plus f at 4 plus f at 6 plus f at 8, all the way dot dot dot, you get the idea, all the way up until f at 2016. Well, breaking it up into these formats helps us add them very nicely, and I'll explain by stacking them one on top of the other. F at 2 is 25 plus 10, right? The next one, F at 4, was 2500 plus 100. The next one, F at 6, was 250000 plus 1000. And then F at 8 was 25000000 plus 10,000. So, and then it just keeps on going like this, plus dot dot dot. So as you can see, when you add all these up, these guys, these ones, the ones with the 25s in them, will be basically a whole bunch of 25s, 25, 25, 25, like that, dot dot dot, 25. And then these ones will be a whole bunch of ones, 1, 1, 1, 1, all the way down to a final 0 at the end. And what we have to do is find the sum of the digits. Okay, well, the sum of the digits shouldn't be too big of a problem because there's no carries here. So no carries exist here. So we can just find the sum of the digits of this guy and then add it to the sum of the digits of that guy. Well, this one here looks like it's 1008 25s, right? Because you are adding F at 2, F at 4, F at 6, F at 8, all the way up in 2016. So it's every even one. So it's not 2016. It would be 2016 divided by 2. So that's why it's 1008 25s. And then this one here looks like, again, it's 1008, but this time 1008 ones. Okay, there shouldn't be a problem to add up the sum of those digits. So we've got 1008 of those 2s. This is now the sum of the digits. So sum of digits plus 1008 times those 5s plus 1008 times those 1s. So that's going to be 2016 plus 5040 plus 1008. And that is 8064. 8064 is the answer to this very challenging question, and that would be choice E.